For 2 decades, enterprise technology relied on a single, massive intake system. Organizations funnel vast oceans of data away from where it's generated, sending it through long-haul networks to be processed by hyperscale cloud data centers. But routing every byte back to a central server breaks down under the demands of the modern digital economy. When you deploy autonomous robotics or smart manufacturing lines, relying on a distant hub to process data and return a decision creates operational delays those systems cannot survive. The solution is an architecture known as modular edge computing. Instead of sending raw information to a remote cloud, this approach shatters the central hub, relocating computing power, storage capacity, and networking resources directly to the physical endpoint where the data is actually generated. This local execution relies on specialized intermediary hardware. Deploy micro data centers on factory floors, virtualized servers into retail backrooms, and rugged IoT gateways on farms. The decentralization of physical compute infrastructure significantly lowers the financial barriers to entry. This shift allows agile, small-scale organizations, particularly cultural hubs and green tech incubators, to access enterprise-grade computational capabilities without the massive capital expenditures of the legacy model. Pushing processing to the network's periphery provides an asymmetric advantage to grassroots labs. By operating at the edge, these organizations can iterate on localized innovation, while legacy institutions remain encumbered by the structural constraints of centralized hub-and-spoke IT architectures. The core vulnerability of a centralized cloud model is a matter of strict physics, the silent bottleneck of latency. This chart tracks latency and power. Legacy cloud introduces a fatal 500 millisecond delay. Edge architecture drops this to 5 milliseconds. Sending raw sensor data upstream saturates bandwidth. Conversely, ARM edge processors require merely 100 microwatts of power, contrasting the full watt required by cloud centers. This massive discrepancy is rooted in Landauer's principle, a physical law mapping the minimum energy required to erase a bit of information. Pushing the computation physically closer to the data source drastically optimizes this physical energy expenditure. By eliminating long-haul transmission and minimizing local power draw, localized edge systems achieve a 10,000 times efficiency advantage over sprawling centralized megacampuses. This physical efficiency radically alters the capital equation. Instead of constructing multi-billion-dollar megacampuses, organizations deploy intelligent edge nodes inside existing industrial buildings or retail backrooms. In applied sciences, providers engineer lab-in-a-box solutions, like this modular container equipped with advanced cleanrooms that operate in a fraction of the time required for traditional construction. This diagram shows local-first behavior. The micro data center processes data directly from the IoT array, functioning autonomously if network connectivity fails. By integrating solar panels and battery storage, green tech incubators construct smart grids that manage power locally without pinging remote servers. These networks function as virtual power plants. An aggregator uses artificial intelligence at the edge to dynamically shift stored communal energy loads during peak demand periods, completely bypassing the need for carbon-intensive peaker plants run by legacy utility companies. By orchestrating local renewable power alongside local data processing, agile incubators achieve true infrastructural sovereignty. They isolate themselves completely from the high latency and physical fragility of the centralized national grid. Legacy institutions possess near-limitless capital, yet they struggle to adopt these hyper-efficient systems. Their failure stems from deep structural paralysis. In this comparison, legacy IT relies on massive manual workloads and rigid silos locked into monolithic procurement cycles. Deploying autonomous AI here carries massive risk, stalling modernization. Conversely, edge-native infrastructure sidesteps this friction. Utilizing modular software, startups execute zero-touch provisioning. Through robust automation, a lean team of 5 developers can securely deploy hundreds of new edge nodes, uniformly update security, and monitor performance remotely. They never have to dispatch a human technician to a physical site. For decades, massive institutional scale was an insurmountable advantage. Today, that exact scale is a structural burden, preventing the rapid iterations and software-defined agility native to edge-deployed incubators. The rapid deployment of distributed hardware has generated an entirely novel economic framework, decentralized physical infrastructure networks, commonly known as DePIN. DePIN utilizes blockchain governance to coordinate real-world hardware. Independent operators supply physical resources, like wireless antennas. Cryptographic algorithms mathematically verify their work, and end users purchase access via digital tokens, incentivizing expansion. To observe this framework, we look to emerging markets. Nairobi, Kenya, known as the Silicon Savannah, is aggressively utilizing decentralized infrastructure to leapfrog legacy development stages. In areas facing severe structural constraints, localized incubators leverage these decentralized networks to bypass traditional telecommunication monopolies and their prohibitive fees, creating crucial economic lifelines. A prime example is Tunaponda.net in Kibera. Traditional internet providers charged exorbitant monthly fees that effectively locked low-income residents out of the digital economy. Recognizing this bottleneck, the Tunaponda Institute bypassed the providers entirely. They deployed a low-cost, community-owned wireless edge network, utilizing unlicensed spectrums to directly link local schools and youth centers. Crucially, they host high-volume e-learning platforms entirely on the local edge internet. Because the data processing and storage occurs strictly at the edge, the community completely avoids the expense of routing traffic through the global internet. This hardware requires continuous cultural scaffolding. Hubs like the Blockchain Center (NBO) incubate local development teams, training engineers to build applications tailored for low-bandwidth environments. Through edge networking and decentralized incentives, emerging markets do not have to wait for multinational conglomerates to lay physical fiber. They simply step over the entire multi-billion-dollar centralized phase of digital evolution, constructing self-contained, sovereign economies. Distributing physical compute across thousands of remote locations presents an acute operational challenge. It entirely shatters the defensible enterprise security perimeter. Unlike virtual assets locked in biometrically secured data centers, edge nodes frequently reside in accessible public spaces or outdoor enclosures. This drastically expands the attack surface, exposing the hardware to physical tampering, direct firmware extraction, and serving as a pivot point for lateral network infiltration. Organizations must abandon the concept of a protected internal network. Instead, they implement aggressive zero-trust architectures, operating under the baseline assumption that every single remote node is constantly compromised. This requires a highly automated framework known as DataSecOps. By automating robust encryption and tokenization directly at the data layer, sensitive intelligence is partitioned and secured locally, never relying on a distant, centralized firewall. While edge computing strips away financial barriers to entry, it demands a highly sophisticated security posture. Data protection can no longer be an external perimeter. It must be written directly into the infrastructure's DNA. As modular edge systems mature, they are rapidly converging with the next impending architectural evolution: quantum classical hybrid computing. Historically, quantum computing required immense, cryogenically cooled facilities, restricting access to a few elite legacy institutions with centralized monopolies over the hardware. But the industry is now pivoting toward quantum-centric supercomputing. In this model, quantum processing units act as modular accelerators alongside classical GPUs, dynamically engaging to solve extreme mathematical bottlenecks. This leads directly to quantum edge computing, the integration of these advanced processing units straight into localized edge networks. In this framework, a grassroots green tech lab can execute extreme complexity tasks, like simulating new battery materials, directly on local hybrid hardware, bypassing the years-long waitlists for legacy supercomputer access. As computational energy efficiency and DePIN frameworks mature, the structural advantage of centralized cloud data centers is eroding. Digital infrastructure is increasingly defined by localized sovereignty and distributed scale.